So usually that's OK to do. There may be some algorithm that you can come up with that doesn't do that somehow. But yeah, I mean, OK. So here's an example that doesn't exactly work that way. If you're doing some sort of quantum walk, and you're interested in whether it's reached a particular node that has some property. And so you measure, is it at this node? And the thing is that it doesn't, when it reaches that node, it doesn't actually stop, right? If you're not measuring, right? It can continue to walk away and then come back later. And so you really can get interference between the terminated and non-terminated cases. So the way people usually deal with that is they'll kind of modify the graph so that the node that you want it to terminate in has some kind of trap where it can go down some extra path that's very, very long. And so it's unlikely to come back. And then you kind of just can see whether it's in that path or not. And that's generally OK.
Could it even be that we do something similar for what we did with ECCs, where it's like if we measure that it's terminated, all the non-terminated states actually disappear, and so we only are left with those terminated states?
I mean, yes. So you measure whether it's terminated, and it's certainly the case that you will collapse. By doing that, you'll collapse. And so if you measure that it was terminated, yes, it will be terminated. My point was that by adding this extra measurement, you may be modifying the outcome, right? So if you kind of, like in Grover's algorithm, if you measure it too early and say, oh, do I have a marked element yet? Then you're killing the superposition that you need. So maybe that's a good example of when not to do it. But if you do it at the right time, then you're getting, with high probability, you're getting information that you want. OK? Other questions? OK. So then what I want to talk about today is some more information theory stuff, starting with channel capacities of noisy channels. So yesterday, I showed you Shannon's source coding theorem, which is a noiseless coding theorem. And so Shannon basically invented the mathematical field of information theory, of mathematically quantifying information. Obviously, people had information before then, but they didn't know kind of as rigorously how to talk about it and how to quantify it. And so he had two main theorems, and one of them was the source coding theorem that kind of said how good you could do at compression. And the other is the channel coding theorem. Which says how good you can do basically at error correction. And so channel coding theorem works in a slightly different regime from what we were talking about on Monday and Tuesday. So on Monday and Tuesday, I guess Monday was where the classical error correction was. We talked about kind of a small number of bits that we wanted to send. And so we encoded it using some extra bits. And we were going to assume that there was at most a certain number of errors, because the probability of there being more errors than that is smaller. But Shannon's channel coding theorem works in kind of the asymptotic regime, where you're sending many, many bits. And the statement is, suppose we have a scheme to send, let's see, so in this case, let me change that to k bits through a noisy channel. And so we're sending many bits probably in a single block, and very, very large block. And we'll assume, again, IID noise. So in the case of a channel, that means that it's just doing some separate noise operation for every bit that gets sent through. and it's always the same. And it has asymptotically zero error, logical error. As we get to very large systems. So the first part of the channel coding theorem says you need at least some number of bits. And there exist schemes using this many bits. And moreover, it tells you what this C is in terms of properties of the channel. So C is the channel capacity. Because it's giving the capacity for how many bits you can send. C is given by this formula, the maximum over input distributions x of I of x, y. Y is the distribution, the probability distribution given by applying the channel to x. So you put in bits with the distribution, or larger registers with the distribution given by x. The channel does some noise to them. You get some other probability distribution out. That's y. And then I of xy is the mutual information. And it's equal to the sum of the entropies minus the joint entropy. Okay. So let me maybe examine this. So suppose x and y are the same, right? And the point is that then they're completely correlated. It's not that the distributions are the same. It's that you put in a bit into the channel and you get out the same bit. So then h of xy is just equal to h of x and h of y. And so this mutual information is h of x, right? So that's saying that the capacity for that particular channel is very high. It's equal just to the total entropy of the stuff you can put in. Yeah, maybe I did this wrong. Yeah, something wrong here. OK, let's see. Hold on. Yeah, OK, sorry, that's right. Yeah, OK. Sorry, I was just a little confused. But C is free. I mean, if you're sending a bit channel, C is going to be less than 1. So this is more. That's what I was confused about. OK, so anyway, so the point is that if the channel doesn't do anything, then the mutual information is just the entropy of kind of the thing that you put in. And in that case, the maximum is in fact going to be taken by the uniform distribution, right? But in general, if there's some noise in the channel, then x and y will not be perfectly correlated. And so the mutual information gets lower, right? So that's why, and in the case where the x and y are totally independent, where the channel just throws away x and does some other thing in its place, then this mutual information is 0. And you can't send anything through the channel, which means you need infinite bits, right? So, yeah.
When you've got an order of k there, it's surprising, like the first term is also order of k as well.
This is supposed to be little o. So it's strictly subleading.
Okay, right.
Yeah. OK? So the upshot of this is that each time you use the channel, you can send C bits on average in the limit where you're using it many, many times. And the fact that this is something that you can easily calculate by just doing some optimization over this input distribution is really useful in practice, right? Because you say, well, I want to communicate. I can try to figure out what the channel is, and then just do some calculation. And I know what my goal should be for error correction. And of course, this was published in 1948. So the subsequent 67 years, it's seen a big growth in digital communications. So there's been a huge amount of effort applied to error correcting codes. And a lot of it is coming up with good codes that kind of get close to the channel capacity of the specific channels. Good means, first of all, that they meet this, but also that they require little computation to do error correction and to encode. OK? Yeah?
I'm a bit confused about the asymptotic error rate.
Yeah. So the statement is probably as strong as you might imagine, which is I'm sending these k bits using, say, n bits. They go through the channel. They come out, I decode. And I want the logical error rate to be close to 0, meaning exponentially close to 0 generally. And by that, I mean I want the probability of having an error in any of the bits to be 0. I mean, when you're encoding bits in a block code, generally, if something goes wrong, it could go wrong on a lot of them. But you can come up with codes where it kind of localizes the errors. And if there's a logical error, it might only affect a few logical bits. But in this case, I'm not even assuming that. I just don't want any of the logical bits to be wrong.
So the number of logical errors per logical bit goes to 0, and 0 make your message longer.
That's true, but most of it is, I mean, it's even stronger than that, right? The number of logical errors total goes to 0. The probability of a logical error on any bit goes to 0. But because it's going exponentially fast, if I insist on that going to 0 exponentially fast, then it doesn't really matter whether I divide by k or not, right? That's just a linear term. Yeah?
Is that a reasonable expectation to have? Like, in my mind, the longer
well, you might, yeah, I mean, you might think it's surprising, but in fact, it's achievable. Okay, and that's one thing this theorem says to you. And the reason for that is like I said, if you're encoding in a block code, if something goes wrong, it's actually going to go wrong on many things at once. But the thing is that by encoding in a very big, well, OK, so here's the basic idea. OK, so you have a very big block code, and so you have n bits, and you have some error rate p. So you're expecting about pn bits to go wrong. Okay, and with high probability, it will be pn bits plus something order square root of n. But the probability of getting p plus epsilon n bits wrong is exponentially small in n. Actually, it's a Gaussian, right? There's a kind of Gaussian tail. So that's what we're working on. So we're coming up with a code that corrects typical errors. It doesn't actually correct the worst case error. It corrects typical errors, a typical set in the same sense that we talked about yesterday.
Also corrects the PN errors, but not like.
Yeah, so it corrects PN errors, but it doesn't necessarily correct every error of length PN. It just corrects one that are kind of randomly distributed. But you can pick a set of errors with total probability exponentially close to 1, and then find the code that corrects them.
So we're wanting that property for our scheme, not for our channel.
Yeah, so this is, yeah, that's right.
Okay.
The with asymptotic logical error rate refers to the scheme.
Okay.
Oh, okay.
That makes a lot more sense.
Right, OK, I see.
Right.
OK. Other questions? OK, so it turns out you can do kind of the same thing for quantum channels. But the answer is not as good. So we have a quantum channel capacity. And so the basic statement is similar, that we want to send k qubits through a noisy channel. And let's assume that it does some CP map independently for every transmission. And we want the asymptotic logical error rate to go to 0 as the number of qubits goes to infinity. And there's some capacity such that to send k logical bits, we need k over c plus little o of k qubits. So the thing is that the quantum channel capacity is much trickier to calculate. So to do that, I have to introduce kind of what the correct analog of this mutual information is. I mean, you can just write down the same formula that would, s of x plus s of y minus s of xy. That's the quantum mutual information. And that has some interesting properties, but it's not the right answer for this, for a couple of reasons. First of all, for this thing to make sense, you need x and y to exist simultaneously. But here, x is the input, and y is the output. And in the classical case, that's OK. You just keep a copy of the input, and then you have both the input and output together. In the quantum case, we can't do that. Although maybe you have some idea from yesterday as to how we're going to solve that, which is by adding a reference system. But the other thing is just that it's not the right formula for the quantum case. So anyway, the thing we want to do is define the coherent information. And the coherent information, so we're going to have, again, this picture where we're sending something through the channel, and we have a reference system R. So let's see. So this is the noisy channel. And so the coherent information is going to be defined as so this is going to be, okay, let me write this as superoperator E. And so if we have the state rho for A, we purify rho to psi. And so trace over R of psi is rho. And the coherent information is equal to S of E of rho minus S of basically this whole output state, which is E tensor I of psi where this is acting on the second system. Okay? So this is the entropy of this output state minus the entropy of the joint output state with the reference system. The identity. So we've done nothing to the reference system, and we've done the channel to A to get B.
RS is E rho tensor I.
E. No. E is so the psi is a joint entangled state. So this is a state of system AR. Okay. So there's another way to rewrite this coherent information, which so what this channel is doing, it's doing some super operator, which we can write, remember, by purifying it, by saying there's some environment that interacts unitarily with the system, and then we're tracing out the environment. And so there's another system E here that's getting some output. And since the psi is a pure state, so let's call this R prime here. So the entropy, so this over here is still a pure state, right? This started as a pure state. This is a unitary interaction now. So this is a pure state. And remember that the entropy, for pure state, the entropy, if you divide it in half, is equal. So the entropy of R prime B, which is this thing, is equal to the entropy of E. So this is equal to S, basically S of B minus S of E. Okay? So you can think of this as kind of the information that Bob's getting minus the information that the environment gets. It's not really quantum information. But the difference is kind of the secret, the stuff that's secret from the environment. And that turns out to be exactly the amount of quantum information you can send through the channel. But there's some additional optimization you have to do. And so the quantum channel capacity is given by this formula. So limit as n goes to infinity, the supremum over rho. But now, well, OK, of 1 over n, I of rho e tensor n. So rho here is not a state of one use of the system, of a system that you're sending through the channel. It's a state, possibly an entangled state, of many uses of the channel. So it's on the Hilbert space A tensored n times. Okay? And then we want to take the average. So we're dividing, we're taking the best thing. If we use the channel n times, we're taking the best thing we can do for those n times. But of course, then we can send n times as much information at least. So we're going to divide by n to cancel that out, and taking basically the average. And then we want to take the limit as n goes to infinity. Okay? So this formula is, so this is sometimes known as the LSD theorem, because for Lloyd, Shor, and Devitak. But convenient set of initials.
They need to write more theorems.
Huh? They need to write more theorems. Well, yeah, it was kind of not even a joint project. It was kind of separate things, but spread over a number of years. So anyway, the formula that we get here is not nearly as useful as the classical formula for a couple of reasons. So first of all, it's a bit harder to do the maximization over rho because it's data. This formula is kind of not as nice a formula to optimize. But the other thing that's maybe more important is that we have to take this limit as n goes to infinity. So this classical thing is what's known as a single letter formula. Well, single letter formula, because you only have to maximize over an input distribution for one use of the channel. So that's kind of a finite size problem. Whereas this one is, you have to look at an unbounded number of uses. And so one idea here, one way you can understand this, so the basic problem is that this coherent information is what's called super additive. meaning that if you're doing it on entangled state inputs here, you can do better than just doing tensor product inputs. And the reason behind that is basically because of the phenomenon of degenerate quantum codes. That in some cases, by putting special inputs, you can cause errors to kind of collapse. So, sort of the one intuition behind the classical channel capacity is that basically what this mutual information is telling you, then the channel capacity is telling you, is how much entropy does the channel add into the system. Okay? It's adding some entropy because of the noise. And so you need to leave enough space in the channel for that to happen, and the rest of it you can use for your information. But in the quantum case, by choosing your inputs appropriately, you can make some errors degenerate, and so the channel is adding less entropy. And in fact, we know specific channels where if you just kind of take a random code without taking this limit as n goes to infinity, you get one value. But if you use appropriate degenerate codes, you can do just a little bit better. Yeah?
This becomes like a kind of an upper bound, right?
Right. So the channel capacity is both an upper and a lower bound.
Right.
In the sense that we know there exist schemes that achieve the channel capacity, and you can't do any better than channel capacity. Yeah. Now, that's kind of a tautologous statement, because it's just saying, well, there's a best value you can do. The non-tautologous statement is that this formula actually gives the channel capacity.
Yeah, right. So, like, I mean, because you're limited by your channel capacity and also, like, your ability to actually encode information in the right way.
Now it's true that any particular scheme you come up with could be well below that.
Yeah.
That's correct.
Yeah.
So that's the sense in which it's an upper bound.
Yeah. So it's not like, I mean, I guess my point is it's not like you, for any kind of applications, it's not that important that you are able to calculate the channel capacity exactly, because it just kind of gives you something to aim at when you're getting your computation.
Right. But the fact that we can't calculate it for a lot of kind of normal quantum channels is kind of annoying, because we don't know what to aim at. Right. We don't even know really how close we are in a lot of cases.
Yes.
OK? So any other questions about channel capacities? OK, so then let me move on to quantifying entanglement. We'll talk about measures of entanglement. OK, so suppose we want to say how much entanglement is in a state. This is something that's actually obsessed a lot of people in the field of quantum information over the years. I mean, we should start by figuring out what kind of entanglement means to us. Right? So what does entanglement mean? Well, it's some sort of correlation that's stronger than classical correlations. Right? We know about Bell inequalities, so that's one notion of entanglement. So we want it to be something that's purely quantum, that doesn't exist out of just classical resources. Okay? But the other side of that is that it's clearly something that involves at least some separation in the states. Right? So at least two people, they have some qubits, and then we talk about the entanglement between them. Or we can talk about the entanglement, multi-party entanglement between 3 people, 4 people, whatever. I'm just going to focus on two-party entanglement. So we're going to have Alice and Bob again, and they're sharing together. They're sharing some kind of quantum state. So when is that entangled? When is it not entangled? What does it mean for it to be entangled? So what we'd like to do is we'd like to say the state is entangled if it can't be created using just classical non-local resources. Obviously, Alice could do something by herself and make some arbitrarily complicated quantum state. And when we think of that, we might say it's an entangled state. But it's not entangled with Bob. Right? It's just Alice doing whatever she's doing. And similarly for Bob. So tensor product state that's OK. So anything that Alice does here that doesn't create entanglement. Anything that Bob does here, that doesn't create entanglement. And moreover, Alice and Bob can make measurements and send classical communications to the other person. And that's also not going to be able to create entanglement, right? That's just a classical resource. So that's classical communication. So anything that they can do with these is known collectively as LOCC, local operations and classical communication. Okay? And so when you're talking about entanglement, the class of LOCC operations is a very important one. Now, LOCC is kind of a complicated class because you can even include multiple rounds of communication. Like Alice can make a measurement and then send the result to Bob, and Bob can do some complicated unitary and do another measurement and send the result to Alice. And you can keep on going back and forth for many, many rounds. But it is relatively easy to characterize a set of states that you can make out of kind of nothing using LOCC. And that's the separable states. So rho is separable if it can be written as a mixture of tensor product states. Yeah, rho AI and tensor rho BI. OK? So certainly, you can immediately see that you can make any state of this form using LOCC, right? Because Alice can say, OK, I'm going to pick a random number I according to the probability distribution PI. And then I'll create the state rho AI. And moreover, I'll send I to Bob. And then Bob will create rho BI. Okay? And that does, in fact, make this state. Now, it's maybe a little less obvious that this is all you can do using LOCC. But probably the easiest way to do that is to say, well, OK, so they run some protocol. Their class of communication, we can just copy that down and convert that into some number I. Right? And then for that particular value of I, they had to just make a tensor product state, because they're just doing some sequence of local operations on either side, including measurements. And so for that I, they'll have a tensor product state like this. And then that's how you get this. OK, so it's just then a question of what's the probability distribution of the possible transcripts. OK. So questions on this definition? OK. So, oh, yeah.
So this can change the entanglement, but only lower it, right?
That's right. So that's the idea. And that's about what I'm going to say next. Okay. So now when we want to talk about quantifying entanglement, we want to say, well, we have in a state a given amount of entanglement, but we shouldn't be able to make more entanglement by LOCC. Mm-hmm. Right? That's the intuition, that if we could make more of it by LOCC, then it's not really entanglement that we're making. It's something else. And so that notion is the notion of an entanglement monotone. So entanglement monotone is some function, f, taking quantum states to, and it's going to be generally some non-negative real number. Okay. And we'd like the value 0, so when this is 0, if you have the following property. So for separable states, we should have f of rho is equal to 0. Okay? So there's no, our quantity tells us there's no entanglement there. And we'd also like it to be non-trivial, so we should have that f of rho is greater than 0 for some entangled states. Okay, I'm not going to insist that f of rho be non-zero for all entangled states. If it is non-zero for all entangled states, then it's what's known as a faithful entanglement monotone. But I want to consider the possibility that we'll have some monotones that characterize some kinds of entangled states, even if they don't necessarily tell you everything about entanglement. And the reason for that is because there are some interesting ones that have that property. OK, so the next thing I want to say is that suppose Alice and Bob have some state rho, and then they do some local unitaries. Right? So no measurements, no classical communications, just unitaries. Well, that's just changing a basis. It shouldn't really change the amount of entanglement between them. So I want to say that it's invariant under local unitaries. So f of UA tensor UB, rho UA dagger tensor UB dagger should equal f of rho. OK? And then the third one is kind of the main one, which is that f of rho is non-increasing on average under LOCC. So this on average is important because suppose you have a state that's kind of not very entangled, even a pure state. So like, 1 minus epsilon 0, 0 plus epsilon 1, 1. Now, it turns out there's some measurements you can make on the state that, with some small probability, will give you a maximally entangled state. Most of the time, it will not. It will give you either an unentangled state or a very low entangled state. But the point is that there's some sort of gambling you could do with this state, where you make this measurement, and there's some chance of getting a state with more entanglement. Okay? So it is possible that to have a specific outcome that increases entanglement when you do these measurements. But on average, the entanglement is not going to increase. Okay? And this, of course, is the kind of the main thing that what gives the name monotone here, because this property is monotone under LOCC. Okay? Yeah?
Why do we allow for a decrease in f of rho?
Right. So here's an operation that's allowed in LOCC, which is Alice and Bob each take their part of the state, and then they throw it out and replace it with a brand new 0 state. Okay? So they could go from a highly entangled state into a tensor product state. That's allowed by LOCC. And we want that to be a decrease, obviously. So that's why. But with unitary stuff, where no information is being lost, we want to stay the same. So that's why these are separate conditions. Yeah?
When you talk about not increasing on average, if I take a POVM or something, or sorry, like a POVM where, because that is a measurement, and I apply that to my density matrix, but I don't do state updates, so like I don't update it based on the outcome of the measurement, then does do entanglement monotones always decrease on the full density matrix?
You mean strictly decrease?
Strictly decrease, sorry, like strictly non-increasing. Right? They might stay the same if you start.
Yeah. Okay. Sorry. So you do a POVM, but you're averaging over outcomes, or not?
I guess I'm just not applying state update, which is the same thing.
Right? Well, I mean, so if you're averaging over outcomes, then basically you're in this on average realm, right? I mean, if you're post-selecting, but saying, oh, there's some different amplitude. I mean, there's some, it's a non-normalized density matrix, which then you can kind of talk about that. Whether your formula even makes sense for that or not is a question. But then you have to be careful.
Cool.
Yeah.
Could you repeat the example for each to the increase?
Yeah. So okay. So the problem is I haven't actually told you any entanglement monotones yet.
Oh.
So let me do that for a moment.
Okay.
So, so first, let me mention, I mean, I said I haven't told you any, but in fact, you have seen one, I think. But one that only applies for pure states. And actually, this example is the main reason that I put the on average in there. So, so for pure states, so we have Alice and Bob. And remember that the entropy of Alice's side is going to be equal to the entropy of Bob's side. And so if you take this pure state, then entropy of Alice's side is known as the entanglement entropy. And it's a pretty natural measure of entanglement. And in fact, it satisfies these properties. Okay? Certainly, if you do some local unitaries, I mean, the entropy was invariant under unitaries, period. So we're taking the entropy of Alice's side. So if we take UA tensor UB rho UA dagger tensor UB dagger, then we're tracing over Bob's side, and we have a UA rho Alice UA dagger, and the entropy is invariant under unitaries, so it stays the same. If we have for a pure state, the only separable states are tensor product states. And so Alice's side is also pure. And so it has zero entropy, and so zero entanglement. That makes sense. And then finally, if we do measurements, so this is the non-trivial part, is that if you do measurements, then the entropy will not increase on average. And that's something that needs to be proved. It's basically a convexity property. I always forget if it's convex or concave in this case. But in any case, and so then the example where you need the on average is if you have a state that looks kind of like this. There's some measurement you can make, which is kind of a slightly rotated 0 plus epsilon 1 versus orthogonal state measurement. And with some small probability, most of the time that will not do anything useful. It'll give you, I remember, a tensor product state or something that's not very entangled. But with some small chance, you'll get a maximally entangled state out. OK? And so that means that with some small probability, you have something where the entanglement entropy is actually increased. It's gone up to 1. But most of the time, it's decreasing. And so on average, it's staying the same or decreasing. OK?
So both Alice and Bob are making measurements here?
So actually, I think it turns out that only one of them needs to make a measurement. Sorry, it's been a while since I looked at this protocol. And I mean, then she can tell, if Alice does a measurement, she can tell Bob what the result was. Yeah, maybe it's not. Yeah. Okay. Right. So this entanglement entropy for pure states is not only a pretty good measure of entanglement. It's basically the only measure of entanglement. I mean, with some additional assumptions, you can come up with any other entanglement monotone that satisfies these assumptions, which is like asymptotic behavior as you take many copies. And they're all equivalent, some function of the entanglement entropy. It also has operational meanings, like you saw, I believe in the tutorial yesterday, you did a problem on entanglement concentration, right? And so that's an example of an LOCC protocol, right, where you start with some large number of non-maximally entangled states, and you're trying to concentrate them down into a smaller number of maximally entangled states, right? And so this is exactly what an entanglement monotone is good for, is telling you how well you can do that, right? And as you saw, the entanglement entropy captures exactly how many maximally entangled states you can get out of it. Okay? Is that, you remember that from yesterday? Long time ago, I know. Okay. But unfortunately, for mixed states, this thing starts to not look like such a good measure anymore. And there's a couple of reasons for that. I mean, so the second property still holds, right? That's the argument I gave didn't really depend on it being a global pure state. But the problem is that already even the first property is failing, right? Because if you have a tensor product of mixed states, then Alice's entropy is going to be non-zero, even though the state is unentangled. And moreover, this statement is not true anymore. So you'd have to choose between Alice's entropy and Bob's entropy. Okay? And so basically, it just doesn't work. We want to go to a more sophisticated measure of entanglement. And unfortunately, then it's no longer unique in the sense that I said. There's actually lots of different measures of entanglement that are kind of good for different things. So let me give you one of them. So this would be the entanglement of formation. So the entanglement of formation is the minimum over pi psi I of sum over I pi s of So you see it has this, this is S of A for the state psi I. So it has this entanglement entropy inside it. And what I'm doing is I am minimizing over decompositions of the state rho. Right? We think of rho as a mixed state. It's a mixture of some set of pure states. That's not a unique decomposition, however. And so I'm going to take the best decomposition, the one that requires the least total entanglement, and then calculate that, or the least average entanglement, averaged over the possible states. OK? So that makes sense. This is telling us the least amount of entanglement needed to create this state via an LOCC protocol. Right? Because again, we can do this LOCC protocol. We take this decomposition. We say, let's, with probability I, we pick the state psi I. And then we're using S of the entanglement entropy of psi I to do that. OK? Unfortunately, oh, yeah, OK. Before I say that, let me just point out why this is an entanglement monotone. So it's unitarily invariant because if you, well, OK, so first of all, it's 0 for unentangled states. That's clear. Because then you just create the best option here. You take the separable decomposition, and then you get 0 up here. It's unitarily invariant because if you make a unitary rotation on these psi's, then you can just do that unitary, sorry, if you make a unitary rotation on rho, you can carry that through to a unitary rotation on the psi i's. And that doesn't change this formula. Now, under LOCC, well, this is the best protocol to create the state rho using LOCC. So if you were able to increase the entanglement of formation, so suppose you could go from rho to sigma and increase the entanglement of formation this way. Okay? Then you'd have a protocol that would, what's the best protocol to make psi? Well, you can always at least do, let's make rho, and then convert it to sigma. And convert to sigma, right? And so the amount of entanglement needed to make sigma has to be, at most, the amount of entanglement needed to make rho. Okay? So that shows you that this is an entanglement monotone. It can't increase under LOCC. Okay, unfortunately, it has some bad properties as well. And in particular, it's not additive. So if you have two entangled states shared by Alice and Bob, then the amount of entanglement needed to make them both together can be less than the amount of entanglement needed to make them separately. So, I mean, this expression, the fact that it's less than or equal to is apparent, again, because you could just make them separately, and this is how much entanglement you need. But the fact that it can be strictly less is not at all obvious, and it took a long time to figure that out. But the upshot is that it means that this thing, while the formula is a property of the state, it's kind of not really an intrinsic property of the state, right? It depends what the context is of the state. So if you're just trying to make the state by itself, this is the right formula. But if you want to make many copies of the state, well, it might be better to do that. So you might be able to save on that. And so people will talk about the entanglement cost, which is the regularized version, in just the same sense that we looked at the regularized coherent information for the channel capacity. And so the entanglement cost is the limit as n goes to infinity of 1 over n times the entanglement of formation of n copies of the state. Okay. Now, even this doesn't really solve the problem. I mean, it's still the case that if you want to make two different states, then the entanglement cost for that is not necessarily equal to the sum of the entanglement costs. So there's still some subadditivity going on. But at least it takes out some of that. And of course, the other problem with this is that, again, it involves one of these infinite maximizations, where you take the limit as n goes to infinity, and that's not something you can do numerically to figure out the actual value of it. Okay? Any questions on the entanglement of formation?
Is there an additive entanglement monotone?
There are. Let me give you one more non-additive one, and then I'll tell you an additive one. So another non-additive one is the distillable entanglement. So the distillable entanglement, so the entanglement of formation said, let's take the best protocol to make this state and count how much entanglement we needed to make it. So distillable entanglement is answering the opposite question, which is how much entanglement can we get out of the state? And we'll insist that it's in the form of maximally entangled states. Okay, so we're going to take the state. We're going to do the best LSCC protocol we can to try to get maximally entangled states. And on average, how many maximally entangled states do we get? Okay, so let's see. So again, it could be, it's certainly the case that if we have a separable state, we're never going to get any maximally entangled states out. So its first property is satisfied. It's unitarily invariant because, well, if there's some unitary, we can do the same protocol and just undo the local unitaries first. That's allowed. And then it's non-increasing under LOCC because, well, suppose we could convert rho to sigma using LOCC, and we can get some amount of entanglement out of sigma. Well, then we can get at least that much entanglement out of rho by first converting to sigma. Right? So again, it's an entanglement monotone. What's not at all obvious is that it's different from this entanglement of formation, or at least of the entanglement cost. And again, you can ask, for the one-shot distillable entanglement or for the regularized distillable entanglement. It turns out, well, certainly it has to always be less than or equal to the entanglement of formation, right? Because otherwise, you could start with some maximally entangled states, use them to make the state, and then distill out somehow more entanglement than you started with. So you're making entanglement out of nothing. That's not correct. So it's less than or equal to the entanglement of formation. Yeah?
How does it satisfy separable states having entanglement 0?
Oh, because if you start with a separable state, there's no LSTC protocol that you can do on the separable state that will give you a maximally entangled state. Right? And so this is saying, how many maximally entangled states do we get? Well, the answer is 0.
Okay.
But it turns out, in fact, that the distillable entanglement can be strictly less than the entanglement of formation. In fact, usually it's less than the entanglement of formation. That it can take more entanglement to make a state than you can get out of it. That there's some kind of inefficiency there. And moreover, there's even something called a bound entanglement, where the distillable entanglement is 0. So you can't get any entanglement out of this. But the entanglement cost is non-zero. And this can be the regularized distillable entanglement and the regularized entanglement information. Okay? So these bound entangled states are entangled states. We need entanglement to make them. They're not separable. But we can never get any entanglement out of them, or at least not maximal entanglement out of them, via LSTC.
By regularized, do you mean the cost?
Yeah, that's what I wrote here, the entanglement cost. So the average over trying to make many copies at once. It still requires, asymptotically, it still requires some entanglement to do that. Right? There could be some entangled states which I'm not sure if there are or not, actually. But in principle, there could be states where making one copy requires some entanglement. Making 2 copies requires less than twice as much. Making n copies requires enough less than n times as much. That is, n goes to infinity. The entanglement per copy goes to 0. Yeah, so I'm not sure whether or not any such states exist. There are people around here who definitely will know. But, yeah.
We talk about bound entanglement. You've got so that's just you take the entanglement cost and you subtract the distillable.
No. So specifically, the bound entangled states are states where the distillable entanglement is 0.
Right.
Strictly 0.
Okay, sure.
Okay. Now, in general, also, the distillable entanglement, well, it's not subadditive, it's superadditive. So it can be that you can get out more entanglement by doing an LSTC protocol on multiple copies of the state than you could on one copy. Yeah, so distillable entanglement is also related to the quantum channel capacity and quantum error correcting codes because you can think of this as correcting errors, right? Suppose Alice creates a maximally entangled state and sends half of it through a noisy channel. Well, then what they get out is a mixed state of some sort. And suppose via LOCC, Alice and Bob can distill some maximally entangled states. Then once they've done that, Alice can use it to teleport whatever qubits she wants to Bob. Okay? And in fact, it turns out that if we insist on protocols, LOCC protocols, LOC distillation protocols, where Alice is sending information to Bob, but not vice versa. Bob is not sending anything back to Alice. That for many channels, that's exactly the same as the quantum channel capacity. But when you have protocols where Alice and Bob can both talk to each other, then they have a bit more freedom. And it turns out that frequently the two-way distillable entanglement is higher than the one-way distillable entanglement of the quantum channel capacity. So to kind of give you a picture of where these different things fit in. Yeah, so let me end with one last measure of entanglement, which is an additive one, and that's the negativity. I mean, I understand that in a previous class you saw the concurrence in a tutorial, was it? So that's another example of a measure of entanglement, although I'm not sure it's even defined for many qubits, so I'm not sure if you can say whether it's additive or not. So negativity. So negativity takes advantage of some properties of operation called the partial transpose. So suppose you have a density matrix. Well, it's a matrix, right? So you can take the transpose. But that doesn't do anything, right? The density matrix is from Shannons. So nothing very interesting is going to happen when you take the transpose. You get another density matrix, which is converted basically I to minus I. But if you take the partial transpose, so you have a two-party system. So now the density matrix is kind of block diagonal. And so the partial transpose is not taking the transpose of the whole thing, but taking transposes of these blocks. So say you take the transpose on Bob's side. Okay?
You can only do it like the diagonal, the leading diagonal blocks, right? Do it on the off diagonal.
No, I think you do it in the off diagonal blocks too, if I'm not mistaken.
You're not going to get a density matrix.
That's right. That's the whole point, in fact. So partial transpose is a map that's positive, but not completely positive. And so if you take it to, if you apply the partial transpose to a tensor product state, well, that's just applying the transpose to one side, right? So that we know we get something positive. We get another valid density matrix. But if you apply it to part of an entangled state, it can give you something that's in general, it does give you something, not always, but often it does give you something that's not a density matrix, that has negative eigenvalues. Okay? That's what it means to not be completely positive. Okay? So that observation makes this a way to detect entanglement. Right? You look at the density matrix, you take the partial transpose. If it's still a density matrix, well, then it might not be an entangled state. But if you get something negative, if you get negative eigenvalues, then definitely it's an entangled state. Okay? So the negativity is then the sum of the negative eigenvalues under partial transpose. Okay? And it turns out, I believe, that it doesn't matter whether you take the partial transpose on Alice's side or Bob's side. You get the same value here. And so the negativity, it turns out, is in fact an additive quantity. It's maybe not immediately obvious that it's an entanglement monotone, but it is. Unfortunately, it's not faithful. And so there are some entangled states which are positive under partial transpose. And in fact, those states are necessarily going to be bound entangled states. Why is that? Well, because they're entangled states, they have non-zero entanglement cost. But they have no distillable entanglement. How do I know that? Well, a maximally entangled state is negative under partial transpose. So if I look at the negativity of the maximally entangled states that I would get out of the distillation protocol, it's non-zero. But the negativity of these original states is 0, right? And we know that negativity can't increase under LOCC, so we can't have had a protocol that converted these non-negative states into maximum entangled states. So the distillable entanglement must be 0 as well. Yeah?
So if we were to treat this as like we could take any state and break it up into these bound entangled states and some non-bound, like whatever the other space is. We could measure each of those individually, and then we would have at least one part being additive, and then another part that describes the bound entanglement part.
Okay, so sorry. So you mean using the negativity to measure the non-bound entangled states?
Yeah.
Yeah. So first of all, actually, it's an open question whether there are any bound entangled states that have non-zero negativity. It's a long-standing open question, and probably there are, but that hasn't been proven. So that's an NPT bound entanglement, negative partial transposed bound entanglement. But even disregarding that, yeah, I mean, normally when people talk about entanglement measures, they want to just kind of have one thing that they're using at a time. If you have these two separate things, it's a question of how you're combining them or switching between them. I mean, just being able to tell whether something is a bound entangled state or not. I mean, so is a difficult problem. Obviously, telling whether it has non-zero negativity is not so hard. It's something you can just compute. But distillable entanglement and the entanglement cost, things like that, are very hard to compute because they involve these infinite maximizations. But moreover, actually telling whether something is separable or not is also a very hard problem. It's an NP hard problem to say whether state is kind of close to a separable state or if it's really an entangled state. So that's another thing that you'd like to get out of entanglement measures is a clean way of telling whether, I mean, yeah, of whether it's actually entangled or not. But okay, I'm well over, but since this is the last lecture, questions? I mean, I'm not leaving town or anything, so you can still ask me questions after.